Diophantus of Alexandria, a text and its history. Norbert Schappacher ***. Footnote. Following a short course I had taught in Strasbourg, I gave on May 29, 1998 a talk at the yearly Euler Vorlesung in the Old Theater in Sanssouci Park at Potsdam, entitled Wer war Diophantus? Who was Diophantus? A write-up of this talk, with added footnotes, appeared shortly afterwards in Mathematische Semesterbericht 45 halves. The publication was in German since the talk had been prepared in German for a German audience. During my visit to India in December 1999–January 2000, I was based at Tata Institute, Mumbai, but spent 1 week at the Chinna Mathematical Institute, during which Professor Seshadri asked me to also talk on Diophantus in Madras. This and a similar talk later on in Bombay provided the occasion to write up the present English version of the paper. It is not a translation but a rewriting of my earlier text, with quite a few modifications. For instance, I omitted certain allusions, e.g., to Karl May, which cannot be understood by anybody who has not been steeped in German culture. On the other hand, I heeded some critical advice that I have received after the publication. For instance, I am glad to correct my previous ignorance of Otto Neugebauer's contribution to the dating of Heron of Alexandria, which was kindly pointed out to me by several readers. I also added quite a bit of material here and there. On the other hand, the introduction to my original Potsdam talk was not deemed fit to print for the Mathematische Semesterbericht. It does not translate well into English. So I insert it here, in the original version, simply for the pleasure of those readers who do understand German. Ein Freund und College, der vor einigen Jahren den Leibniz-Preis verliehen bekam, und der mit dem Kanzler seiner Universität zu jener Zeit nicht auf gutem Fuß stand, sollt mir von dem Telefonanruf mit dem dieser Kanzler ihm zu der großen Ehre des Preises gratuliert. Der Geert College nam nat erlichen, dass der Kanzler sich nunmehr eins unter Figurentuns ihm gegenüber befleißigen Werdals das Beste in der Fall Joasen war. Stattdessen aber nahm der Kanzler die Eröffnung Diophantisker Probleme in der Preisbegründung zum Anlass zu fragen, dieser Diophantus, auf den Gene Probleme durchzuergingen, den Joasen sei, und wann gelet habe. Der Erfolg der Frage war total. Der College was nichts Genos und war somit von dem Verwaltungsbeamten wieder einmal in die Defensive gedrängt. Was ein SIE geantwortet? Viel leicht meinen SIE konnten auch dann nicht in dies Verlegenheit kommen, wenn sich die DFG entschließen sollt, ihnen den Leibniz-Preis zu verleihen und amlich deshalb nicht. Weil SIE in ihrer Arbeit kein Diophantisches Problem gelöst haben. Aber heute, nach dem erfolgreichen Beweis des großen Fermatschen Satzes durch Andrew Wiles, kann jeder Mathematiker, gewissermaßen auf der Straße, befragt von einem x-beliebigen Bekannten, in dieselbe Verlegenheit geraten. Denn die besagte Fermatsche Vermutung war bekanntlich in Randbemerkung in einer Ausgebeter Arithmetica eben Genis Diophantus. Und was sagen SIE dann, wenn man SIE fragt? Wer war Diophantus, und was haben die Diophantisken Probleme mit Diophantus zu tun? *UFR de Mathématiques et d'Informatique, 7 Rue René Descartes, 67084 Strasbourg CEDEX, France, Schappa at math.u-strasbg.fr. 1. Abstract. Diophantus's Arithmetica is one of the most influential works in the history of mathematics. For instance, it was in the margin of his edition of Diophantus that Pierre de Fermat, some day between 1621 and 1665, wrote the statement of his so-called last theorem, which was proved only a few years ago. But Fermat was not the first to derive inspiration from Diophantus's collection of algebraic arithmetic problems. The Arabs had profited from reading the Arithmetica when developing algebra as a mathematical discipline. Nor was he the last. At the end of this paper we present the example of a Berkeley PhD thesis of 1998 which is directly inspired by a problem of Diophantus. But for all the influence that this author had on various mathematicians at various times, we know almost nothing about him, and even the text of the Arithmetica betrays very little of what Diophantus actually knew or did not know. We first present views of well-known historians who speculated on who Diophantus was, then go on to describe some salient features of the Arithmetica, and finally we survey the main different readings of this text that have been given over the centuries. First in the Arab world in the 9th and 10th century, and during the Byzantine Renaissance, 11th to 13th century, then during the 16th and 17th century in Western Europe, Sixet, Fermat, up to the 20th century way of looking at Diophantus. 1. Dating Diophantus. 2 works have come upon us under the name of Diophantus of Alexandria, a very extensive collection of solved problems entitled Arithmetica, and a short, more theoretical treatise on polygonal numbers, which is rather Euclidean in style. 1. The Arithmetica are essentially self-contained, at least as far as we know them. They do not contain any explicit reference to other mathematical authors. Point 2. On the other hand, we know of only one mathematician of the pre-Arabic and pre-Byzantine era who quotes from Diophantus's Arithmetica. 1. For the treatise on polygonal numbers, see the Greek-Latin edition Tannery 1893/95, vol. I. 450-481. Polygonal numbers are triagonal numbers, i.e., numbers that can be arranged in triangular shape, like 1, 3, 6, 10, 15, 21, or perfect squares, or pentagonal numbers like 1, 5, 12, 22, 35, etc. Thus in general, the sequence of a fold polygonal numbers is given by the rule n2. 2 plus n, 1, a, 2, for n equals 1, 2, 3. 283 places, which all occur in Book V from the Byzantine tradition. See below for the numbering of the books. The text refers to porisms. See Tannery 1893/95, vol. I. 316, 6, 320, 2, and 358, 5. It is not clear whether these results were part of another book of the Arithmetica which is now lost, or if the references are to an independent treatise, by Diophantus, or simply known to Diophantus's intended readers, of which no other trace has come upon us. See also our discussion of general statements in the Arithmetica in section 4. Below. 2. Theon of Alexandria, 3, father of Hypatia, the best-known woman scientist of late antiquity, who however owes her fame not least to the fact that she was gruesomely murdered by street gangs of the bishop and early father of the Kitch Cyril in 415 AD. 4. Theon of Alexandria thus belongs to the middle of the 4th century AD, and this gives us an upper bound for the dating of the Arithmetica, and of their presumed author Diophantus. If we accept, and we might as well, that the same Diophantus was indeed also the author of the treatise on polygonal numbers, then we obtain a lower bound because in this work there is a quote from Hypsicles who lived around 150 BC. See Tannery 1893/95. Vol. I. 470, 27. The known works of Diophantus thus provide us with an interval of 500 years for their composition, and this is about all that we may be certain of when it comes to dating Diophantus of Alexandria. No reliable biographical information about him is available. 5. The great French classical scholar and mathematician, Paul Tannery, 1843–1904, to whom we owe, among other standard works of reference of the time, see for instance his Fermat, the monumental critical edition. Tannery 1893–95 of the 6 books of the Arithmetica which we have from the Byzantine tradition. Discovered in the library of the Escurial a letter of the Byzantine intellectual Michael Psellos 6 which has been used to date Diophantus more precisely, see Tannery 1893–95, vol. 2, 3742. In this letter, Psellos mentions work on arithmetic, the Egyptian method of numbers, as he calls it, by a certain Anatolios which was dedicated to Diophantus, c. Tannery 1893–95, vol. 2, 38, 22, 39, 1. Tannery identified this author with the historically known Anatolius of Alexandria, a philosopher who was the bishop of Laodicea, an ancient town on today's Syrian coast, around 270–280 AD. And who was indeed the author of a treatise on arithmetic of which we have fragments. Assuming a treatise can be dedicated only to a person still alive, this would put Diophantus in the 3rd century AD. But considering the late date and the nature of the Psellos source, the sentence itself which mentions the dedication is slightly corrupt in the Manu. 3 SE Tannery 1893–95, vol. 2, 35, 9–11, cf. vol. I, 8, 13–15. 4 The year 415 is undisputed. There are, however, diverging opinions about the age at which Hypatia met her tragic death. See for instance Gielska 1995. 5 Note that, even though such an uncertainty of dates may seem enormous for the historic Mediterranean cultures, in the history of Indian culture and science, for instance, even larger intervals of uncertainty are the rule rather than the exception. See for example Gupta 1995, p. 263f. 6 Michael Psellos, 1018–1081, was for many years a philosopher at the court of Byzantium and authored a great number of works on a broad variety of subjects, from philosophy and theology to the sciences and alchemy. Aside from numerous letters, he was maybe best known for his lives of various emperors and politicians, which take a psychological approach to the personalities portrayed. He liked to present himself as influential, although he and his group lost their leading position under Constantine IX in 1054. At times he lived as a monk. 3. Script: one may want to be skeptical about these conclusions. It actually seems that Tannery got somewhat carried away with this letter that he had discovered. He used it as his only basis for emending the single most important methodological statement of the Arithmetica, in which Diophantus introduces his symbol for the one and only unknown that he can handle in his notation. 7. Still, independently of the Psellos letter, the fact that, as far as we know, nobody before Theon mentions Diophantus, and also the fact that the problems of the Arithmetica are rather unusual in classical Greek mathematics, make it probable that Diophantus wrote his works rather towards the end of the 500-year interval. Today, he is generally said to have lived around 250 AD, as Tannery's argument suggested. There is also a mathematical papyrus in Greek from the 3rd century, not by Diophantus, but which uses the same symbol for the unknown that we also find in the Byzantine manuscripts of the Arithmetica. 8. But one ought not to forget the basic uncertainty in all these conjectures. In fact, a lot can be and has been said in favor of relating Diophantus closely to Heron of Alexandria, an encyclopedic author of texts on questions of mathematics, and in particular on applications of mathematics. Heron also discusses problems similar to those of Diophantus, and both use the same notation for the minus sign. If one assumes a close relationship between the two, one may even wonder, as Sir Thomas Heath did, whether the Dionysius to whom the Arithmetica are formally addressed was maybe identical with the addressee Dionysius of Heron's book on geometric definitions and of his elements of arithmetic. The dates of Heron, after having been hotly debated for a long time, seem to have been settled by Neugebauer via the computation of a certain lunar eclipse in Rome mentioned in Heron's treatise on the diopter, according to Neugebauer. Heron was alive in 62 AD. 9 Should this lead us to place Diophantus up to 2 centuries earlier than is generally 7 SE Tannery 1893/95, Vol. I. 6, 3-5. Instead of leaving this sentence as it reads in all the manuscripts, i.e., as defining the A, O, A, O, the untold number, the number which is as yet unknown, to be what has none of these special properties that were discussed in the preceding lines, like the property of being a square, cube, etc., but simply holds some multitude of units. Tannery wanted us to read, in Ivor Thomas's English translation, Thomas 1941, p. 523, the number which has none of these characteristics, but merely has in it an undetermined multitude of units, is called arithmos. But the untranslated last word of the Greek sentence that Tannery created simply means number, thus rendering the statement at least very awkward. This criticism of Tannery's correction of the crucial sentence was made in a very convincing way by Rashid and Allard. See the note on the Arabic word for the unknown, say, in Rashid 1984, Tome 3, 120-123. 8 PAP Michigan 620. I owe this reference to Garrick 1984, p. 143. 9 FOR The relation between Heron and Diophantus, see Heath 1921, p. 306, Note 1, as well as the long footnote 149 in Klein 1992, 244-248. Neugebauer's argument was published in 1938, after Heath and after the original German version of Klein's book. See Neugebauer 1975, p. 846f. 4. Done today? A little mathematical poem which claims to be the inscription on Diophantus's tomb almost strikes me as a parody of our ignorance. It determines the length of Diophantus's life by a linear equation to 84 years. 10. There are obituary notices also for Nicholas Bourbaki. So this poem need not deter anyone from speculating that Diophantus was in fact the name of a collective author. On the other hand, there is no positive reason to embark on such a speculation, and most of all, I do not see how any of the difficult questions related to Diophantus would thereby become easier to answer. 2. Speculations on Diophantus's origins. Just as the precise dates of his life, Diophantus's ethnic or religious affiliation is open only to speculations. The possibility to speculate has been extensively used by many authors. Let us give some examples. Hermann Hankel, in his work on the history of mathematics in ancient and medieval time, adopts an almost poetic tone when he comes to Diophantus 11. Here, in the midst of this sad and barren landscape of the Greek accomplishments in arithmetic, suddenly springs up a man with youthful energy, Diophantus. Where does he come from? Where does he go to? Who were his predecessors? Who his successors? We do not know. It is all one big riddle. He lived in Alexandria. If a conjecture were permitted, I would say he was not Greek. If his writings were not in Greek, no one would ever think that they were an outgrowth of Greek culture. Around the same time, the German historian of mathematics Moritz Cantor 12 confessed that, to him, Diophantus, with this name which is frequent in Greece, was a true Greek, disciple of Greek science, if one who towers high above his. 10 Se Tannery 1893/95, Vol. 2, 60f. In Y. Thomas's translation Thomas 1941, p. 513, this tomb holds Diophantus. Ah, what a marvel! And the tomb tells scientifically the measure of his life. God vouchsafed that he should be a boy for the 6th part of his life. When a 12th was added, his cheeks acquired a beard, he kindled for him the light of marriage after a 7th, and in the 5th year after his marriage he granted him a son. Alas! Late begotten and miserable child, when he had reached the measure of half his father's life, the chill grave took him. After consoling his grief by this science of numbers for 4 years, he reached the end of his life. It is a poem from the Anthologia Paulatina of mathematical problems in poetic garb. The interpretation which Harder admits in Harder 1995, 267f, to the effect that the solution is 65 plus 13 years rather than 84 is compatible with the German translation that Harder uses, but not with the Greek original. 11 Hankel 1874, 157. For the original German quotations of this section, see also the published version of this talk in Mathematisk Semesterbericht 45 halves. Hankel is of course well remembered as a mathematician, for instance for his integral for the gamma function, Habilitationsschrift Leipzig 1863, and by his Untersuchungen über unendlich oft oscillierend und unstetige Funktionen, Math. Annalen 20, 1882. 12 Cantor 1907, 396. The first edition of Cantor's work dated from 1880. 5. Contemporaries. He was Greek in what he accomplished, as well as in what he was not able to accomplish. But we must not forget that Greek science, as it conquered the East from Alexandria, brought new ideas back home from these campaigns, that Greek mathematics as such has never ceased to pick up whatever it found worth picking up here and there. Paul Tannery himself did not speculate on the ethnic origin of Diophantus. However, he suggested one may identify that Dionysius, to whom the Arithmetica are addressed as Dionysius, Bishop of Alexandria, and deduce from this that Diophantus was Christian. 13. For Oswald Spengler, the author of the most successful, and terribly politically influential German book of the 1920s, Der Untergang des Abendlands, The Decline of the Occident, Diophantus was a crucial indicator of the change of culture that, according to Spengler, took place in late antiquity. Much like Toynbee after him, Spengler undertook a parallel, cyclic description of the big cultures of world history, in each of which he claimed to be able to recognize the same morphological developments. Spengler battled the idea of universally valid mathematics. For him, the mathematics developed by a culture are a particularly telling indicator of the type of this culture. Late antiquity for him was no longer part of the classical culture, but belonged already to the Arab culture which, according to Spengler, was characterized by the magus Ches Weltgefühl, the magic apprehension of the world. This culture would later on find its religion in Islam. The Pantheon in Rome, for instance, was thus diagnosed by Spengler as the earliest of all mosques. Now, Diophantus's Arithmetica stand out because of their formal, algebraic rather than geometric treatment of quantities, which prompts Spengler to comment 14. This is indeed not an enrichment, but a complete negation of the Weltgefühl of antiquity. This alone should have sufficed to prove that Diophantus is no longer part of classical culture. A New Zealand fuel, a new notion of number, is at work in him. What an undetermined number A, an unnamed number 3 is both neither quantity, nor measure, nor line segment a Greek would have not been able to say. Diophantus lived around 250 AD, i.e., in the 3rd century of Arab culture. Spengler, who must have had his own way of recognizing truly great works, unperturbed by detailed mathematical scrutiny. Mathematical qualities of Diophantus, he would not let himself be impressed by a collection of tricky problems that have but inspired later writers. 15. To be sure, Diophantus was not a great mathematician. Most of what his name sings, and what there is surely not quite his own invention. His accidental importance lies in the fact that, as far as we know, he was the first in whose works the New-Zealand fuel is recognizable beyond any doubt. Diophantus being a clear representative of the new, magic culture, Spengler even proceeded to make him comply racially with this role. While Spengler categorized the philosopher Spinoza as the latest representative of the magic Welt fuel, in fact a latecomer, for the simple reason that he came from the ghetto, i.e., since he was Jewish. 16 He turned this argument around in the case of Diophantus, whom he had already introduced as the first representative of the magic Zelange fuel. Forgetting even that he had previously said that Diophantus was not a great mathematician. 17. How many of the great Alexandrians may have been Greek only in the magic sense? Were Plotin and Diophantus maybe of Jewish or Chaldee origins? David M. Burton. The most absurd statement about Diophantus's origins that I have been able to find generously conflates different historical eras and transposes the often conjectured influence of Babylonian problems on those found in the Arithmetica into ethnic categories. In Burton's History of Mathematics from 1991 one reads 18. Diophantos was most likely a Hellenized Babylonian. 3 in the text. All these quotes use the absence of biographical information in order to make metaphorical statements about the Arithmetica by way of speculating on the origin of their author. I claim that the same phenomenon which we see here with respect to Diophantus's biography repeats itself with respect to his mathematics. The Arithmetica are almost as elusive as their author. The way in which mathematicians through the centuries have read and used the Arithmetica is always a reliable expression of their proper ideas, but never can we be sure of what these readings tell us about the text itself. The Arithmetica are probably the most striking example of a mathematical text which, on the one hand, has inspired, and continues to. 15 Spengler 1923, 98/99. 16 cf. Spengler 1923, 391. See the wonderful ironic comments on this by Leonard Nelson in Nelson 1921, 115 117. 17 Spengler 1923, 770. The Chaldee dynasty, the last Babylonian dynasty, as of 626 BC, were Aramaic families that were generally respected as learned people. 18 Burton 1991/95, 223. I have thus far searched in vain for an author who suggests that Diophantus was black African. 7. Inspire generations of mathematicians at various different moments of the history of algebra and number theory, but which, on the other hand, has never, for all that we know, be developed further as such. At least mathematicians tend to find it hard to admit this. We are convinced, are we not, that, if we peruse the text sufficiently carefully, we can practically look over Diophantus's shoulder while reading the Arithmetica. But this text, with its unique history of different readings over the centuries, provides a particularly good example to demonstrate the problems of this naively optimistic mathematical attitude. I will thus succinctly survey 4 major historic occasions on which a group of mathematicians or learned people rediscovered the arithmetica. In fact, since we have no original parts of the text, nor any direct knowledge of what happened to it between its first writing and the 9th century AD, all we can talk about are rediscoveries of a text that had slipped into oblivion. Such a rediscovery may conveniently be called a renaissance of Diophantus for the time and place where it occurs. I will suggest that there were 4 major such renaissances of Diophantus so far, or more precisely, 2 times 2. All the parts of the arithmetica which we possess today go back no further than to the first double renaissance, the 2 chapters of which took place in Baghdad, RESP in Byzantium, between the 9th and the 13th century. The twofold Second Renaissance comprises the appropriation of the arithmetica in Europe and the Western world as of the 16th and 17th century. For a few observations on the text of the arithmetica. Before turning to the First Renaissance and its 2 chapters, however, let us try to take a brief look at the text itself. Of course, strictly speaking, this is impossible. There is no original text of Diophantus which has not somehow passed at least through the first double renaissance. And from the main thesis I am defending here it should be clear that I have no illusions whatsoever about the feasibility of simply reading the text 19. This being said, one does of course have to look at it. And the reader of Diophantus then finds himself in a situation somewhat analogous to that of Hardy and Littlewood when they were perusing Ramanujan's manuscripts sent to them from India. 20 Both texts clearly show a virtuoso author who is able to solve problems some of which, in the case of Diophantus, are not easy to solve today for, say, a good first-year university student of mathematics. For Ramanujan the level is of course even higher. But both texts are also 19 The subtle way in which André Vey seems to indirectly acknowledge this problem in his book Vey 1983, his brief chapter on Diophantus is placed in Chapter I. Proto-History, X, pp. This allows Vey to treat Diophantus essentially by way of various looks cast back on the arithmetica from later developments of number theory. 20 I am indebted to Don Zagier for this nice comparison. 8. Written in a way very different from what we are used to, and, above all, they contain notoriously few hints at the underlying general methods that the author has employed to find his solutions. This makes it extremely hard to pin down explicitly what he knew. But it will be convenient for the reader if we briefly point out a few properties of the arithmetica which are good to have in mind when looking at the further voyage of this text through history. Let us take as a very easy example problem I.28, find 2 numbers whose sum and the sum of whose squares are given numbers. The context reveals that by number Diophantus always means positive rational number. Before solving this problem, Diophantus states a necessary condition. Twice the sum of the squares minus the square of the sum of the 2 numbers has to be a square of a positive rational number. Nowadays, using algebraic notation and knowledge which dates back at most to the 16th century, we would probably reconstruct this somewhat like this. We look for x and y such that x plus y equals a and x2 plus y2 equals b. Then 2ba2 equals x, y, 2 equals y, x, 2 does indeed have to be a square. And a moment's thought shows us today that this condition is also sufficient, for y equals a x transforms x2 plus y2 equals b, divided by 2, into the quadratic equation. x2, x plus a2, b2 equals 0 of discriminate 2ba2. 4. If we want, we can then find the 2 rational solutions of this equation expressed in terms of a and b, from the formula we have learned at school. Diophantus has no such notation, nor was there any general notion or theory of quadratic equations that he could have been taught at school. It is also not completely clear whether he understands his necessary condition, which is clearly stated as such, in fact as a necessary and sufficient condition for the solubility of the problem. 21. All he does is solve the problem, and here is what solving means for him. First he chooses the value 20 for what we have called A, and he chooses the value 208 for what we have called B. Note in passing that 2 times 208 to 202 equals 42 is indeed a perfect square, so the necessary condition is respected. Then Diophantus proceeds to use his only notation for 1, and only 1 at a time, unknown quantity. 22 Following tannery, let us write x for this. 21 The necessary conditions stated for other problems of the arithmetica tend to be necessary and sufficient to ensure the general solvability of the problem as stated in positive rational numbers. But at times the divergence of the generality of the statement and the particularity of the given solution make the logic more involved. The first such instance occurs with problem I.21, and was already remarked as such by Bachet. Cf. also footnote 34 below. 22 According to a generally accepted hypothesis of Heath's, his sign for this was probably originally a contraction of the first two letters, A, of the Greek word for number. A. O. 9. Unique unknown that Diophantus can handle notationally. Diophantus then writes the difference of the two numbers, the bigger one minus the smaller one, in the form 2x. In other words, x plus 10 will be the bigger, and 10, x the smaller of the two numbers we want. Then, noting explicitly that 10 is half the first given sum, this leaves him with the following equation 23. 208 equals, x plus 10, 2 plus 10, x, 2 equals 2x2 plus 200. Note that it very conveniently does not have a linear term, and therefore immediately yields x2 equals 4, i.e., x equals 2 since only positive solutions are allowed by Diophantus. The two numbers sought are then 12 and 8. A generous mathematician's way of reading this solution would be to say that Diophantus shows here a general method to deal with quadratic equations. And it is only his restricted notation which does not allow him to spell things out in appropriate generality. He is thus led to choose more or less generic values for the constants, and also for those unknowns which are not covered by x. It is true that Diophantus commands the technique of choosing numerical values to perfection, never losing sight, even in the most involved problems, of which choices have been made at which stage of the argument, and not hesitating to go back and correct such a choice if it becomes apparent that it would lead him to an irrational or negative solution of the principal problem, or of some auxiliary problem along the way. However, it is not clear whether Diophantus was aware, for instance, of a general notion of quadratic equation. He does, in the later books, occasionally indicate more or less general recipes for handling various types of quadratic equations. 24 But the only overriding principle that he seems to have at heart is a ranking of expressions according to species, i.e. essentially, according to powers of x, which occur in them, with a view to transforming the equations at hand in such a way that one is finally left with an equation between two multiples of the same power of x. See the explanations in the introductions to books I and 4.25. And yet more seriously, one begins to suspect that there may be more to those generic choices of numerical values than our understanding with 2-3 to be quite precise. Its anticipated generality made us guess at first sight, when it comes to what we call indeterminate problems, i.e., problems that do not, like the previous one, have a unique solution in positive rational numbers. In fact, in most cases there is nothing in Diophantus's usual treatment of indeterminate problems that shows any difference from the case of determinate problems. Once a single solution in positive rational numbers is obtained, the problem is considered done and Diophantus moves on to the next one. Let us take as example the famous problem 2.8, in the all too narrow margin of which Fermat inscribed the statement, but not his would-be wonderful proof, of what came then to be called Fermat's last theorem 26. The problem reads, partition a given square into two squares. Diophantus takes the given square to be 16, and writes the first square of the required partition as x2. He therefore has to make 16, x2 a square, which we might write y2 in our modern notation. In order to do this, Diophantus will use the ansatz, y equals 2x, 4. This works well because x2 plus y2 equals 16 then becomes 5x2 equals 16x, i.e., x equals 16.